All right, welcome everybody, and we're going to go ahead and jump into chapter 13, and we're going to start talking about AC. Okay. So with DC, the D and the C stand for direct current. Okay. And as I was saying in the Zoom meeting, that looking at a DC signal is very interesting because it's just a straight line. It's a constant. Whereas an AC, right, now AC stands for alternating current. Okay, so we're going to have a positive half of the signal, and we're going to have a negative half of the signal. It's going to repeat like that over and over and over. And so the AC is actually what we use to create electromagnetic waves that travel through space. So part of the transmission that I'm doing right now is radio transmission, right? I'm using an electromagnetic signal because I'm using a lav mic for one thing. From my voice, it gets picked up by the microphone. It gets transmitted down by wire to the device, the transmitter, and then the transmitter transmits an electromagnetic signal to the receiver. The receiver takes it, decodes it, and then eventually it makes its way to your speakers, and then you can hear me. So there's a lot that happens from when I talk to where you hear me, and same thing happens with the video, right? And so somebody may be watching this on their phone on demand or something, and you had to receive your signal either from Wi-Fi or maybe you have 5G and it's coming from outer space or a local cell tower. I don't know. But that's the basis of all cell phones, TV, radio, satellite, communication, radar, radiography. If you get an MRI, right, all of that stuff. When you pop something in the microwave oven, you're creating these really, really high frequency waves in your microwave. Micro is 10 to the negative 6, right? So that is super duper quick. So the way that, you may already know this, but the way that microwave ovens work is that they vibrate the water molecules in whatever food that you're trying to heat up. And they basically rub against each other so quickly that they create heat, right? So that's why some stuff is completely devoid of water molecules and does not get hot, okay? So anyway, and so like it says here, they convey information and power. They have an amplitude. They have, there's all kinds of things that you can say about an AC signal if you know just a few things about it. Okay. Now the reason why I think I've hinted at this before, but the reason why we use AC versus DC is because we can transmit it for long distances. Okay. There's less power. There's less power loss to the transmission over the long distances. If you were to do that with DC, you'd have to have a substation like roughly every mile, okay? And if you had a lot of people pulling off of it, then you might have to have one every half a mile. Depends on the population density, right? So it could be done, and it was done by Edison, and he did it in New York. I forget where exactly. But he powered city streets and a couple of blocks in New York City with DC, but he didn't transmit it over long distances, okay? And so that's why he lost out to Tesla, and you may know the story. There's actually a movie out now called The Current War, and it's all about the Edison versus Tesla, because that was huge back then because, basically civilization as we know it was built on one of these two systems thriving, right? And it was AC because we could transmit it over long distances. We didn't have to have substations every mile, half mile, whatever. And so it was that's why it won out, right? And so Tesla, even though he's not really discussed much, Edison is a much more well-known public figure. Tesla is the one who actually created most of the AC stuff that we know about, and like motor design and using wires, coiled wires to achieve some of this stuff. So he was the pioneer in AC, and Edison lost out. Now Edison still did pretty well for himself. He wasn't just involved in electrical engineering, right? He invented all kinds of things, and so he's not even really known unless you take a class like this. I mean, you might know that he invented the light bulb or something, right? But the big the big thing, and the one thing that stuck in his craw was the fact that Tesla beat him out. And I think Westinghouse is the one who decided to pay Tesla, and they invested in his technology. So there's a, I don't know if they cover this in the, I would assume they do, because it's a huge thing. If you go online, there's still a video of it, I think. Last time I checked was probably 3 or 4 years ago, but I checked, hang on a second. I checked to see if it's still online. Like I said, about 3, 4, 5 years ago, and it's where Edison would go around to these different cities, and he would say, we need to use DC because DC is safer. And to some degree, he's correct. Okay, that's why if you put you shouldn't do this and don't do this, but if you put your tongue on a 9-volt battery, typically it just gives you a little jolt. Okay, it might be a different story if that were an AC signal, right? So, he's trying to convince these people how dangerous AC is. And so what he would do is he would bring out a retired circus elephant. An elephant is a giant creature, and he would take it out in front of a crowd of people. And you got to remember, this is like 1890s, 1900, 1901. So people don't even know what electricity is. They probably rode their horse and buggy to go see this demonstration. And so he says, this is how dangerous AC is. And he would electrocute a live elephant in front of this crowd of people, and they just, they'd be standing there with their jaw open like, well, I don't want that thing in my house. It just brought down that elephant. It'll take care of me even quicker. And so that was his, I don't know how many times he did that. I just know that there's one video of it that survived. And it's only like a 15, 20-second video maybe. I can't remember. But anyway, so it's hard for us to imagine that was such a big controversy because we've been using electricity now for 120 years, right? But even in like the 1920s and right when people started getting electricity in their houses, they would tell their kids to stay away from the outlets because they thought the electricity would pour out onto the ground and was kind of, wherever the outlet was in the wall, that it would just kind of pool in the air because they weren't engineers, they weren't mathematicians, they're just, I don't know what, jobs you could have back then, but more than likely they weren't trained like we're trained. And so it was magic to them. I don't know how this light turns on. Somehow there's something that goes through this wire and turns this light on, right? And if you have no understanding of physics or the atom or electrons or how things move through a conductor, how in the world are you going to understand in 1925 how something like that works, right? Very difficult. So, but anyway, that's why we use AC. Tesla won. I have yet to see the current war, and I can't believe I haven't seen it yet because as soon as I saw it posted that it was coming out, it's even got the guy from from the 1920s, Boardwalk Empire. And I forget the guy's, he's a great actor. I forget his name, but he was in that show as well. Somebody in the comments probably knows. But anyway, yeah, so let's go on to the next slide here. So again, this is, if we're talking about a DC signal, this is what I expect on the right side here, right? It's not very interesting to look at. Okay, it's 6 volts. That's great. It's 6 volts at 1 second. It's 6 volts at 100 seconds. It's 6 volts at 50 seconds. It's always 6 volts. Okay, I don't need a graph to show me that, okay? But, you could have somebody that's outputting a DC signal from, say, a power supply, an adjustable power supply or a variable power supply, and somebody could sit there and turn it up and turn it down, but there's a DC response there, okay? Unless you had somebody that could twist the knob back and forth that went down to the negative DC voltage. If you could have somebody that could do that 60 times per second, then you could, and you'd have to go all the way up to 170 volts peak. You'd have to take it up to 170 volts peak, down to negative, 340 volt switches back and forth 60 times a second. That's what's happening in the wall. But you could, if you had a DC supply and your wrist was quick enough, I suppose you could output a periodic signal, all right? It would look pretty rough on an oscilloscope, but I suppose you could do it. But nobody would do that, right? So an AC waveform, in general, it reverses over time. It can ride on a DC offset, but if you don't have a DC offset, it averages 0 over time. So if you do the calculus on this, essentially when you take, like the integral of something, you're taking the area under the curve, right? And so if you average that over one period, 0 to t, you see that this positive half will cancel the negative half, right? Because this is positive area, this is negative area because it's underneath the 0, right? It's underneath the x-axis. So those will cancel each other out, and they average 0 over time, okay? You may have seen this before in your classes. If you've had physics, you've probably talked about this as well. And, we've talked about the quadrants, long time, right? Ever since algebra, right? Is it algebra or algebra 2? I can't remember. But anyway, quadrant 1 is where everything's positive. Positive x, positive y, right? And so we always start our, if we're going to talk about any kind of angular motion, whether you're talking about a pulley that's turning or whether you're talking about a phasor, right? Or a sine wave for that matter. You start at positive 0. It goes up in a counterclockwise direction. There's 90 degrees, right? 90 degrees is where x is 0 and y is at its highest positive point. And you keep going around. Now I'm into what we call quadrant 2, where x is negative and y is positive. And we get down to 180 degrees. At 180 degrees, that's where x is at its most negative point and where y is at 0. Then we continue on down into quadrant 3. This down in quadrant 3 is where everything is negative, where you have negative x and negative y. And we come down to 270 degrees. And at 270 degrees, you have your most negative y, and x is at 0. And then you come around to completion through quadrant 4, where quadrant 4 is where we have a positive x and a negative y, back to where we started. That's 360 degrees. That's one revolution. So if we think about a sine wave as having multiple revolutions, right, it's going to 360 degrees over and over and over and over and over, if we want to look at it like that, okay? And that's exactly how we look at it. So you can see here's the angular version of a sine wave. It starts here, it goes positive, comes back to 0. Then it goes negative, goes back to 0. Positive. I realize it's going technically backwards, but this is not, this circle here and this right here, this is not, there's no time, okay? We're just talking about x and y. And so, here we go, up to this positive amplitude, and then back down to 0, then down to the negative amplitude, and then back up to 0, okay? So, I mean, there is a time component because how quickly does that happen, right? If you're going very, very quickly, then you're at a high frequency, and that means it takes less time to make one completion, okay? So anyway, that is a sine wave. I know it looks like a circle, but some of you may, I wish I had a picture of it, but the clock in my office is a unit circle. And, instead of 12 o'clock up here, it's 90 degrees. And so it looks like the unit circle, and you just have to know where the hands are supposed to go. But anyway, you have probably seen that before. I just wanted to repeat, okay? Now, if we look at that at voltage on the y-axis versus time on the x-axis, now we can see that same thing happen, and we can see what happens over time, okay? So again, this one over here, we start at 0, go up to the positive y. Here we start at 0, go up to the positive y. And then we go back down towards 0. We go back down towards 0 and cross it. Now we go negative y, right? As we go negative y here, and then we come back to 0, okay? And again, these are all versions of a sine wave. Electromagnetic waves, guitar strings, sound waves, ocean waves, and so we use sine wave calculations and all kinds of stuff. I took a power electronics class where we used it all the time, and I took a, what was it? I just blanked it. Oh, it was a radio class. I can't remember exactly what it was called. It used to be 302. I don't know if it's still available at IUPUI or not, but that was a fantastic class. So if they do, no, 302 is the PLC. It's 304. So if you are going to go to IUPUI, somebody check. You don't have to do this. I might check it later today, but 304, I forget what the exact name of that class is, but if you get a chance to take it, because it was amazing. We built our own super heterodyne receiver, and when we took it out to the window outside the labs, we could actually pick up AM signals from the air. It was pretty amazing. So anyway, so if we're going to talk about the sine wave, then we should probably go ahead and give it an equation that we can work with. And luckily, somebody a long time ago did that work for us. Okay, so the way I would read this is voltage is a function of time, and so we can get the instantaneous voltage at any point in time. Okay, and the equation for that is we take the sine of 2 pi ft. Right, and the way that we break that down, I normally let's see if I can find this here. Symbol, I don't want that omega, I want the other one. Let's see here. Do I have the other omega available? Anyway, the one that looks like a W, right? But it's the omega sign. And so I typically know this as sine of omega t. Right? And you may recognize that from your physics classes, right? When you're talking about like angular momentum and things like that. Okay, but it's that omega right there is always 2 pi f. Okay, and f is the frequency in hertz. Hertz is what we measure. We'll talk about period and frequency and see how they're related. But V is voltage as a function of time. It's the instantaneous voltage at any point in time if we use this equation. Now, if you're going to do that on your calculator, you have to make sure that your calculator is in radians. All right? Now, let's see. I've got mine because we're going to do some calculations here in a second. What did I do with it? I cleaned this up today. And I must have cleaned... Oh, I remember where I put it. Okay. Ooh. All right, so if you have a TI 30 series, all right, I believe there's a key that you can use to put it into radians. It might be in the mode or the menu button, okay? I know for the TI 80 series, it's always in the mode. If you go to mode, and then it says angle. Like for my TI 89, I go mode, and then 1, 2, 3, 4. The fourth one down, it says angle. And you have the option to do radian, gradient, or degrees, okay? Your calculator has to be in radians if you're going to use this equation here, okay? Now, if you were going to do it in degrees is super easy, right? Because you just take sine of 63 degrees or whatever it is. And there is, as you know, a way to convert from radians to degrees. Let me type this here. Anybody know the conversion for radians to degrees? So if I wanted to, there we go. 2 pi equals what? So degrees to radians conversion. You can really use any ratio that you want. Nick typed in 2 pi, but then I would say 2 pi over what, right? I typically use pi over 180 degrees. Okay, so pi radians over 180 degrees. The reason I was asking what does that equal when he said, let's see, pi radians. I'm trying to do this like I would do a computer programming equation. Okay, so pi radians over 180 degrees. Now you could say 2 pi over 180 degrees, or I'm sorry, over 360 degrees, but that just reduces down to pi over 180, right? So you could leave your calculator in degrees if you wanted to, and then just make sure that you always calculate what's inside the parentheses there and then convert that to degrees, okay? So that is an option. Yes, Kofi, 2 pi for 360 degrees, that's right. Like I said, pi over 180 is typically what we use, all right? But you could use either one, doesn't matter. The math will work itself out in the end, okay? So we're going to do some calculations of this here in a second. And again, this is, degrees versus radians. Same thing, you just count degrees from 0 to 360, and, if you're going to do radians, it's 0 radians. And if this is pi, if pi equals 180, then pi over 2 is 90, and 3 pi over 2 is 270. And then you get all the way back, 2 pi is 360. So 0 radians and 2 pi radians are on the same line, right? The same axis. All right, now if we're going to look at the, again, this is not a calculus-based class, but if you look at the calculus of a sine wave, if you take the derivative at different points, you'll see that the amplitude is at, the amplitude goes to, the upward trajectory here, as it slows down as it starts to go back negative, and it's fastest where it goes through the x-axis. So it's quick, slow, and then quick, slow, and then quick, and then slow. So it slows down up here at the top, and it eventually has a 0, right? It's just like if you were going to throw a ball 45 degrees or whatever. Eventually, the y direction is going to be at 0. You're going to have 0 y direction velocity, and then eventually it's going to be negative because it's going to go back in the other direction, right? But for that split second, that instantaneous moment in time, the upward velocity is 0, right? And so essentially that's what's happening here. So the majority of the change from 0 to 45 degrees is this straight line, and it's only the last part that gets crammed into this transition here, okay? Now, if we're going to talk about frequency and time, all right, frequency and period, really, the time it takes to complete one cycle, so here we go. So the time it takes to go, like if you were to start measuring at where it crosses the 0, where it crosses the x, and follow that for one complete iteration, one complete cycle, that is called the period, the length of time it takes to complete one cycle. Frequency says, how many of those can you fit inside of 1 second? And so here's the relationship. Frequency equals 1 over the period. Okay? Essentially, we're talking about cycles per second, because how long does it take to complete one cycle? That's the period. If you take the inverse of that, you figure out how many cycles are in 1 second. Okay, so the higher the frequency, the shorter the period, right? Because you're completing the cycle so quick that you can fit more and more and more of those into 1 second. And so it's an inversion. It's kind of like with, we didn't talk about it, but with resistance and, its opposite as well, okay? If you just take the inverse of it. So, let's see here. So let's do a few of these, all right? And because we're on the shorter delay today, and I'm not using my camera, go ahead and figure out what the period is for the first one, right? WIBC if you follow FM radio, and then figure out what these other two are, all right? And here, I'm going to do this. This last one, I want you to use 16.667. Okay, because it's actually 6 repeating, but I want you to use a couple more decimals past here, so that I can force you to get the right frequency. All right, so go ahead and do these real quick with your calculator. Find the period for 93.1 megahertz. Find the frequency of 10 nanoseconds, and find the frequency of 16.667 milliseconds. Okay, go ahead. So 93.1 megahertz equals, or is the frequency for what did we say? 10.7 nanoseconds. Okay. What about 10 nanoseconds? How about 100 megahertz? Yep. Yeah, so that one, yep, that's it. And again, the hertz is capital HZ is how we list it. So if you did megahertz, it would be capital M, capital H, Z. Yeah, oh, he said, okay, that works too. Okay, what about the last one? 16.667 milliseconds. Oh, Nick says millihertz. Should just be 60 hertz. That's why I'm doing that one in particular, because it is 60 hertz. This is what comes out of the wall. So the period of the frequency that we use for AC outlets is 60 hertz. Okay, and so the period is 16.7 milliseconds. All right, I say 16.667 because it gives you, 59.9 hertz. So Nick, I think you're off by 1,000. Could just be in your exponent in the way you punched it into your calculator. All right. All right, so here's another example. So this time we're going to use the sine wave equation, right? Actually, for this one, I don't even think we need to use it to get these answers. But I guess we do need it for the frequency. He said, I forgot the milliseconds. Yep, that will do it. All right, given this picture right here, tell me what the frequency is, and then tell me what the equation would be if we assume that this is a sine wave, because that is an assumption, by the way. You know, if I just draw you one that looks like one, that doesn't mean that it's to scale and it's accurate and it is a sine wave. It just means it looks like one. But this is, if this actually calculates out to a sine wave, we're assuming that. What is that equation? Okay? So you're going to have some kind of V of t. Well, let's see. One complete cycle takes 2 microseconds, right? So the period is 2 microseconds. You can see that off the graph here. This says that these marks are in microseconds, and so it takes 2 of them to complete one cycle, then 2 more to complete the next cycle. So the frequency of this would be 1 divided by 2 microseconds. Whoops. How about if I, can I have this in black, please? Thank you. So if I do the equation here, so the frequency is 1 divided by 2 microseconds. I don't know why it keeps doing that. Give me, there. Anybody got it? So 2 microseconds is the period for what frequency? I've just typed my answer in the comments, and I will hit enter very shortly. Waiting to see if anyone comes up with it. So 1 over 2 microseconds. I got 500 kilohertz. Okay? And then the question says, what would be the equation for V of t, assuming that this is a sine wave? All right, well, let me make sure that I have my, yep. So this would be the sine of 2 times pi times 500 kilohertz times t. Okay? And so now I should be able to plug in for any time t, I can get the instantaneous voltage if I have my calculator set up properly. Okay? Now, for these two, you don't need that equation to calculate, do you? It says, what is the voltage at 2 microseconds? Well, we have a graph right here. What's the voltage at 2 microseconds? So if I said V of 2 microseconds, 2 microseconds, what would be the voltage? How about 0? Right? Because it's right there on the x-axis where it crosses. Right? That's 2 microseconds. What about 3 microseconds? Well, we go back up to 2.5 microseconds here. I'm looking at time, and then we're at 3 microseconds. Well, the voltage at t equals 3 microseconds is also 0 volts. Right? We're talking about the instantaneous voltage at any point in time. Okay, so I've typed those two answers in the, is that going to let me edit it? No, it's going to let me remove it though. So V of t equals 3 microseconds is 0 volts. Okay. Now here's another one. Now we have, since we've talked about this, all the way back up to, let me find it, all the way back up to here. The thing that I skipped over here says the generic expression for a voltage sine wave with a maximum value of 1. So we're assuming that this sine wave only has a peak amplitude of 1 volt and it goes down to -1 volt. Okay? Now that's not always the case, especially, like just take the example of what comes out of the wall. That's 170 volts peak. Negative 170 volts peak in the other direction. So we have a peak, what we call a peak-to-peak voltage of 340 volts. And we're going to talk about that in just a second here. Okay, but let's look at this. So the peak voltage here is 4. Okay, so what would that equation look like if we have an amplitude of 1? All right, the way that I would write that equation in my notes would be like the following. I'm going to write the generic equation right here. And hopefully it gives me a choice to go. Yep, there we go. All right. So more generically, for all of our AC signals, okay, I would do the following equation. V sub P, which is the peak voltage. What is the highest voltage that signal has? The highest Y value, in other words. Like in this one, it's going to be +4. So it's V peak times what we saw earlier, times the sine of omega t. I'll just do the 2 times pi times frequency times time. Okay? So this is, I'm going to even highlight this because this is what I use for all of mine. All right, is it going to let me highlight it? No, it doesn't want to let me highlight it. That's not nice. Please. Wow, I can't believe it doesn't give me the option to do that. Oh well. So anyway, this will account for all sine waves, no matter what the peak value is. Okay. So if we were going to do one for this, what is the peak amplitude? I would say the peak amplitude is 4 volts. What is the minimum, or the negative peak, if you will? That's -4 volts. What's the period? How long does it take to complete one cycle? Well, I can see here it goes, there's the positive half, there's the negative half back to 0. The period is 1 millisecond. Okay? The frequency is going to be the inverse of that, and so we have 1 divided by 1 millisecond. And if you were to do that calculation, you should come up with 1 kilohertz. Okay? So, that being the case, what is my equation for this? All right, this equals 4 times the sine of 2 times pi times 1k hertz times t. Okay, I can make this, I can take away that space and that space. There we go. So there it is. So this describes this particular equation. All right, so I've got, if I take 2 times pi times the 1k frequency, and then I plug in for any point t, I should be able to get the voltage. Okay? So, well, let's do something with that real quick. How about, what is the voltage of t equals, let's pick one, right? Let's just look at this for a second. Half a millisecond would be right here. That's 0. Anything from 0 to a half a millisecond, or we could look at that as 500 microseconds, right? Anything from 0 to 500 microseconds is going to be positive voltage. Anything from 500 microseconds to 1 millisecond should be negative voltage. So just pick one in between there, pick some value, and then see if you get the calculation correct. Let's go ahead and use, let's do it out here. All right, so how about up here? So this is 1.5 milliseconds. Let's use 1.7, which is roughly right there. So we should get a positive voltage that's closer, or I would say is probably at least half. So I'm going to say probably 3.5 volts is my guess, right? So find it at 1.7 milliseconds, okay? Make sure your calculator is in radians. So find the voltage at t, I'm typing this in the comments here, at t equals 1.7 milliseconds, okay? Go ahead and type that into your calculator and tell me what you get. So again, the equation that you're going to use for this right here is right down here. 4 times the sine of 2 pi 1k hertz times t. Times the sine of 2 times, where's my pi key? There it is. You probably have a pi key on your calculator as well. I don't know where it's at on the, it's always different on every calculator. That one's not really standard. 2 times pi times 1k hertz, so 1e3 for me, times, now I'm going to plug this 1.7e negative 3, because that's milliseconds, and then I'm going to take 4 times that whole thing. What did I say? 1.7? 1.7 is down here in the negative, isn't it? I said between 1 and 1.5, and then I chose a number that's outside of it. So 1.7 should be a negative number. I apologize. 1.5 is right here. Here's 2. Obviously, between here is 1.7, and so that's why we're getting a negative number here. So I should have picked like 1.2 or 1.3 or something like that if I wanted a positive voltage. Okay, so what do you get at 1.7 milliseconds? 3 significant figures. It's going to be crucial that you understand how your calculator works doing these problems. I got negative 3.8 volts. Okay, which makes sense. That's down here, right? And so 1.75, which would be right here. So 1.7 is probably about right here. So that makes sense. Negative 3.8 volts. Okay. As I said, there is a possibility you could ride on a DC offset. And so I think even in your book, they make reference to this peak-to-peak voltage measurement or calculation, okay? You may see something that says the peak-to-peak voltage is 2 times the peak. If we have a signal that looks like this, that is true. However, if you want to, I don't like these special case things. I like to just learn the one method that's good for all things, right? And so I always use maximum value minus the minimum, okay? In this case, since we do average 0 over time here, and there's no DC offset, 4 maximum minus the minimum, so 4 minus a negative 4 gives us 8, right? That is, in this case, 2 times the peak, okay? So in this particular case, that's true. However, in this one, there's a DC offset that it's riding on. You can see that, right? So I don't know how many volts that is up here, but there's an AC and a DC signal together. And when you have that, the AC signal rides on whatever that voltage is. And so you could have a positive DC offset. You could also have a negative DC offset. Wherever that offset is, the whole signal rides on that voltage. If there is no DC signal, then it rides over 0. Okay? And so what number do you input for sin? Sin is a function. Sin is the sine wave function. So you use the sin function on your calculator. Okay, the sine wave function on your calculator is an instantaneous calculation of the sine of some either degrees or radians is essentially what it boils down to. Okay, it's telling you where at on this sine wave you would find the voltage at that particular time. Okay. All right. Let's go ahead and move to the next one here. So what would be the peak-to-peak voltage here? The peak voltage, notice this, the peak voltage is always what the most positive or what the highest level, oh, that's okay, Ben, no problem. The peak voltage is always, always, always the voltage from the 0 axis. So in this case, even though if we pulled this down, this is 6 volts peak to peak. 5 minus a negative 1 is 6. So a peak voltage on something that averages 0 would be 3 volts. This will be shifted down 2 volts. If you shift this down 2 volts, that goes down to 3. If you shift this down 2 volts, you get to negative 3. Okay, so you'd have from 3 to negative 3. But it rides up here on this, apparently that's a 2 volt offset, okay? So peak to peak. Now once you start adding capacitors and inductors to your signals, or to your circuits, you're going to start getting this kind of stuff. You're going to have signals that are out of phase with each other. If you were to look at them, hang on a second here, it says, Salu asked, are there a difference between max value and amplitude value? I think it's best described right here, okay? So peak to peak is always max minus minimum, and the max is whatever the peak is, okay? So I guess another way that you could say this would be the voltage peak minus the voltage minimum, right? Because the maximum is always going to be the peak. Okay, so like here, even though they're riding on the DC signal, the peak is always from the 0 axis, and so it would be V max. So in your equation for your sine wave, it's going to be this peak voltage. Even though it averages, the peak to peak might only be, let's say, 6 volts. This could be 9 volts up here, and 9 volts is what you use because that's the maximum possible that you could find with this, okay? Okay. So, if you have a purely resistive AC circuit, in other words, all you have are resistors in series with or in parallel with your AC voltage source, okay? In that case, everything in the circuit is always in phase because resistors and the current and the voltage source are always in phase with each other. The things that are out of phase is when you start to use inductors and capacitors, as you see down here. Okay? So when you're out of phase, that means when two voltages or currents are the same frequency, but pass through the zero and reach their maximums and minimums at different times. All right? So it's still, you know, you can't have one resistor that has one frequency and another resistor that has another frequency. That doesn't make any sense, okay, unless you had two competing AC sources for whatever reason, okay? Which doesn't even make sense. But, you know, if you have inductors and capacitors, that's where things get shifted, because as we'll learn, inductors and capacitors both store and release energy. And when you store or release energy, that takes time. It's not instantaneous, right? It takes a while for a capacitor to charge up to whatever voltage it's going to charge to. It takes an inductor to get to steady state over a period of time. So sometimes it happens very, very quick, and sometimes it takes a while. Depends on the time constant. That's all going to be covered on Wednesday, at least for capacitors. All right, so you know, we are going to start looking eventually at cases where this is out of phase, right? But for a purely resistive circuit, right, the current and the voltages are in phase. We could have 15 resistors in series here with this 100-volt RMS source, AC source, and they would all be in phase. And remember, just being in phase means that, well, it could mean multiple things. It means that they cross the zero at the same time, they have their maximums at the same time, and they have their minimums or their negative peaks at the same time, okay? That's in a purely resistive circuit. Now, we just introduced this term right here, this RMS, okay? The terms that we've learned so far, peak and peak to peak. Peak to peak is simply max minus min. Peak is always whatever from the zero, from the x-axis to the most high y point, okay? And now we're going to introduce this other one called RMS, all right? And this is where you can find it on a sine wave. And if we were in class face-to-face right now, I would tell you that you should, you know, put this on your crib sheet, because it's got everything on it, right? It's got the positive peak, it's got the negative peak, or I would call they're calling it the negative maximum, okay? But really it's the minimum or negative peak, and this is the positive peak or the maximum, all right? Peak to peak is always max minus min. And then you've got these two other measurements that are on here. One of them is for average, which we will not do at all in this class, okay? So you don't have to commit this to memory or write it down unless you're just interested in it. This will become useful in calculus, right? But not for what we are doing, okay? For us, the measurement that we want to get after is this one right here, the RMS value. 0.707 times the peak. So some of you may recognize that 0.707 as 1 over the square root of 2, right? So if you actually looked at the actual equation, it's 1 over the square root of 2 times the peak, right? Which is the effective value, what we call the effective value. And we'll talk about why that's called that, okay? So anyway, as you travel along here, right, 0.707 times the peak is the RMS. The maximum value is the peak, the minimum value is the minimum, and the average is 0.637 times the peak, but we're not going to concern ourselves with that, okay? All right, so let's talk more about these other values here, all right? So let's look at the average. Again, if you haven't taken calculus before, this is going to make no sense, and so, you know, this is not part of something that you need to remember or you're going to be quizzed on, okay? I just put it on here because people like to see. So Ben asks, so is 120 volts an RMS voltage? It absolutely is. If you take 170 volts times 0.707, you will come up with 120 volts. So your meter is meant to read in sine wave RMS, all right? So when you make, like if you were to take your DMM and put it in 200 volt range, AC 200 volt range, and you plugged it into your outlet, any outlet in your apartment, or your house, then you should read 120 volts RMS. If you look at the actual signal that comes out of the wall, it's 170 volts peak, negative 170 volts peak for the minimum. So that's a 340 volt peak to peak signal, all right? So it's a lot bigger than just that 120 number that we use, all right? So this is the, if we're talking about the average or what's the DC equivalent, essentially. It's 1 over the period, and you go from 0 to the period when you integrate this signal. Okay, and essentially you're just finding the area under the curve. If you have a sine wave that averages 0, that means you had no, if it averages 0, you had no DC offset at all, right? The DC is going to turn into 0, right? But if you do have a DC offset in here, whether it's positive or negative, then you're going to get an average voltage there, all right? So anything that averages 0 over time that has no DC offset, this is going to be 0, okay? But it's always 0.637 times the peak. That's as far as we're going to go with this. You do not have to know this right here for this class, okay? So this is why we talk about RMS, all right? You may be wondering to yourself at this point, okay, we spent 2/3 of the class talking about DC signals, and we calculated power for these DC systems, and I know how to do that. It's voltage times current, okay? How would you compare the power consumption through a DC-powered resistor, like you see over here, versus an AC-powered resistor, okay? Excuse me, I gotta take a drink. So the way that we compare the two is by their heat energy lost, right? I've talked about multiple times with resistors, they're essentially, the electrons are coming like a train through that conductor, right? And they run into that resistor and they have resistance against it and it slows it down, right? Well, that energy that the electrons were coming with has to go somewhere, and so it gets dissipated as heat. And so if you can compare that dissipation, then you can compare the two heats, or you can compare the two power consumptions, okay? So the average power dissipated by the load is nothing more than P equals V times I, where these are essentially the RMS values, the resistor current and the voltage respectively, okay? And again, if you were to look at the average power of a periodic waveform that averages 0 over time, in other words, it has no DC offset, you're going to get 0 over time. You can have an instantaneous power, but the other parts are going to cancel each other out, okay? Okay, let's see here. RMS. So this is the actual equation. So that means root mean square. So we take the square root of the mean, or the average, which is the integral here from 0 to t times 1 over t, and then times the square. So you square it, you integrate it over the period, and then you take the square root of it. That's the voltage RMS. Do the same thing with the current signal. The current is also a sine wave, and so this is I peak down here essentially, right? I peak times the sine of 2 pi ft. That's what that signal is. So you square that thing, integrate it over the period, take the square root, and you'll have the IRMS. Okay, and this is, there's other waveforms too that aren't just sine waves. We have triangle waves, right? Those kind of look like sawtooth. Sawtooth has a different prefix, or not prefix, but a different, I would call this a coefficient out in front, so to speak. Or multiplier, I guess you could say. 0.707 times the peak is the sine. For a square wave, it just is what it is, right? Because there is no transition from, with a sine wave, it goes up to the top and then it sort of slopes down. With a square wave, it's this, it's that. It's this, it's that. It's a very sharp 90-degree turn, okay? And so the peak voltage of a square wave is just whatever the peak is. Or I'm sorry, the RMS is whatever the peak is. For a triangle wave, it's 0.577 times the peak, and for a sawtooth, it's something different. This is the only one, and I may ask you a question like, what's the RMS of a 5-volt peak square wave? And you would say, well, it's 5 volts RMS because it's a square wave, right? That's as far as I would take it for that one. So you might jot that one down as well, but this is the one I'm most concerned about. Again, this is what you get from the wall outlet, positive 170 volt peak, negative 170 volt peak minimum, and one period is 16.6 milliseconds repeating. Okay. All right. Now, again, if you live in Europe or if you lived in parts of Asia, and I'm not sure about Africa or South America. I think South America may be 60 hertz as well. I used to know what more of them were, and I don't know if any of them have converted. I don't know why the world just can't, but you got to think about how many decades has each country or each continent put into the infrastructure behind 60 hertz and 50 hertz. Nobody's changing anything. You can just buy a simple converter these days. And there you go. So if you do have a DC offset, you do have to include that with your AC signal. Now, we are not going to do any of these equations right here, okay? But that is what it looks like with a DC offset. And there you go. And if you wanted, the RMS value, if you had a DC offset, it's the square root of the sum of the squares, is the way I would say that, okay? This is the proper way to say it, but this is really just the square root of the sum of the squares. All right, let's see here. So this is something I wanted to point out. So the meter that you have, the Mastech, is the first kind of meter, okay? Essentially what it does to measure the RMS is it filters out the DC, it detects whatever the peak voltage is of that signal, and then multiplies it by 0.707. Literally, that's what happens in your meter, okay, your DMM. So typically these are only correct for sine inputs, and I don't believe that our meters will do anything but sine waves. I think that's it. I think it'll do frequency, so it'll detect when it goes back to 0. I think that's what the frequency counter does, all right? But anyway, so almost every meter that's, I would say, under a couple $100, that's what they do. Well, now the flukes are true RMS, so I shouldn't say that. There are some flukes that are around $100 that are true RMS that don't just do this, okay? But some of those fluke meters, like the fluke, oh geez, what was it? The 95 fluke 95? Now I can't remember. I used to know every fluke model, manufacturer model number for all these different things, and the farther I get away from my job, I just can't remember them. But there was one that everybody, the Fluke 87, that's what it was, the Fluke 87. That thing is like $400, okay, and it's a handheld device. But that one's got true RMS. That's like the workhorse of industry is the Fluke 87, okay? And I don't mean just for electricians. I mean for manufacturing, for everything. Everybody's got the Fluke 87. That's like the gold standard in industry. And we used to calibrate them all the time. But anyway, but for most meters, like, you can go on Amazon and there's all these different companies. Most of them are based in, Southeast Asia. A lot of them are based in China. And essentially, they have a couple of companies out there, and this is the same for woodworking tools too. They have a couple of companies that make the guts of it. They make the boards and everything. And then they sell them to these different companies, and then they put their cosmetic package on it. But it's essentially the same meter, right? And there's tons and tons of companies. The companies are popping up so fast, I can't keep track of any of them. But brands like Fluke and what else? I guess I don't think they use Agilent anymore. They use HP. I think HP bought them out, right? And there's some other ones that are pretty good too. I know X-Tech has been around for a while. X-Tech is the master of the 20-in-1 meter, where they'll have the DMM, and then they'll also have a light meter and a distance meter and all kinds of stuff. Field Piece is also good. Ben just talked about Field Piece. Field Piece is a good one as well. If you go through our HVAC program at Ivy Tech, that is what they recommend that you get. There's a specific model that's great for HVAC technicians because there's really only a couple of capacitor values. It's the starting capacitor and the running capacitor. I don't know a whole lot about HVACs, but I know that there's a starting capacitor that allows your AC unit to kick on, and then there's a running capacitor that helps maintain that voltage so it has a constant supply of voltage to work from. So when you get a dip, you don't get a power surge through your through your device. It still can happen, but it helps it run more smoothly and efficiently. Okay, so Those are really the only capacitors they need to measure, and the only time they really need to measure current as an HVAC technician is the flame sensors, and they're down in like the 400 microamp range. So they don't need something that measures, 10 amps, because they're never going to measure anything like that. They need something that has a very specific low range current where they can measure their flame sensors. Need to have a capacitor measurement on it, and then AC voltages, right? So that's the main thing that they're looking for. And they use also DC if you have a control signal, okay? So, I forget what it is. I think it's the field piece L17 or something like that, or the L71. I teach 113 also, but I haven't taught it for a year now, so I can't remember exactly what meter it is that they recommend. But yeah, all kinds of different meters. If we were in the lab right now, we actually have bench flukes, the Fluke 45, which is a 4.5-digit multimeter, and it's auto ranging. It's got all these niceties on it, and it is also true RMS. But brand new, those things are upwards of $1,000, okay? So when it comes to electronic measurement, you absolutely get what you pay for. And if I were an electrician, like let's say I was a union electrician for GM, which I know, the reason I say that very specific job is because I know a lot of union electricians at both Ford and the Ford plant that was down in Bedford, and then also, which I think is a GM plant now that I think about it. But anyway, let's see here. So, the Fluke meters, auto ranging, very, very nice, bench top. But they are very, very expensive, okay? So essentially, these are the terms that we want to walk away with from here, okay? Except for this one. Don't worry about that. But everything else, right? And here it is. I thought I pulled this out. Max minus Vmin, okay? Peak is I peak or V peak, could be either one. Peak to peak, it could also be I max minus I min. Okay, don't worry about the average for our class, but 0.707 times the peak, whether you're talking about current or whether you're talking about voltage, okay? All right, yeah, so I was saying earlier about the unit electricians, all right? I have, one of my friends got hit with 400 volts and blacked out and ended up in the hospital. He woke up in the hospital and didn't know what happened, and he got hit with like 440. Because he thought some panel was off or whatever. But anyway, his meter is rated for a surge of, I forget what it is, okay? But it's like he has a Cat 4 meter, and I believe it's 10,000 volts. So if you were going to measure, let's say you wanted to say if one of your breakers was working in your panel, in your garage or whatever, and you take your $10 Menards meter that has no protections in it at all, and you put that thing up there to measure the voltage, and the power company has a surge on the line, that thing might make it to your meter. If that thing makes it to your meter, it will explode and arc flash and burn you with third-degree burns in your face, okay? So on your meter, there's a CAT rating, a category rating, all right? I'm going to go over here and look at our Mastech because I forget what this one is. Okay, so this one does 1,000 volts category 2, 600 volts category 3. So, if I were in industry, if I were an electrician working with high voltages like that, I'm not using anything less than a 4, okay, a Cat 4. If I'm doing the lab work that I used to do at the metrology lab, then I'm okay with a Cat 3, okay? But a Cat 3 at 1,000 volts, not a Cat 3 at 600, because I could still get hurt. And there's videos of it, where people lose fingers and arms and things because of an arc flash in a cabinet. All right, and so that's why you have the different category ratings on your DMM. So that's what I'm saying. I'm not going to take a no-name company that I've never heard of before, and even if theirs is a Cat 3 or whatever, I'm not going to, because these manufacturers, it just depends. Sometimes you'll see the UL, on some of these that say that they were tested, but there has been people who have done independent studies of them, and a lot of them don't do what they say they're going to do. Fluke goes out of their way to make it a priority for safety. They're the ones who come out with all the safety videos that we show in all of our classes. They actually have divisions of their corporation that are dedicated to safety, okay, and to making meters safer. Because, you know, electricians in these big facilities that work with power electronics, you know, they get zapped all the time, and they, you know, sometimes it ends their career, sometimes it's fatal, especially if you're working with great big selector switches in a manufacturing facility like Rolls-Royce, where you have to put on a full bunny suit to even walk in certain areas, right? A full protective flash suit that, you know, by the way, if you get hit, probably isn't going to do you a whole lot of good, except maybe melt the material to your skin or something. It's pretty wicked. Those people get paid what they should get paid, because that's a dangerous job. Because all it takes is one mistake. You have to be perfect your whole entire career. You can't make any mistakes whatsoever, because that could end you, right? I mean, there's other professions where that's the case, but anyway. So again, other common periodic waveforms. You could also do something like this. And if you Google like stepper motor projects or stepper motor do-it-yourself, they use a lot of these type of signals. And I would call this, I don't know if I would call this a pulse width modulated signal, but it doesn't have a 50% on, 50% off duty cycle. So it's been manipulated. This looks like either a one, you know, where it's high for 10% of the time, it's off for 90%. But it's periodic and repeatable, right? So it goes back high for 10 seconds and then it's off for 90% of the time, right? High for 10% of the time, off for 90. High for 10% of the time, off for 90. That is still a periodic repeating signal, okay? It's just that the frequency is different. All right, the frequency is still how long it takes to complete one cycle, but you can't go right into the middle of it and have it be on for half the time, off half the time. That is a straight square wave signal. If it's a square wave, then it's on for half the time, it's off for half the time, or, you know, it goes all the way down here, all right? So it could be positive and then it goes negative. But in this case, it's always V times the peak, which is the RMS for these. And then here's our sine wave. And this dives in more to, you know, changing the duty cycle, you know, 10% on, 90% off, 10% off, whatever. If we're going to put this into multisim, the signals that the schematic symbols that we use are the AC power, which is this one right here, and the function generator. So the function generator, you can actually dial in what type of signal you want. You can have a sawtooth, or I'm sorry, you can have a triangle, you can have a square wave, or you can have a sine wave. And then you can choose the frequency and if it has an offset and what's the amplitude, peak, whatever. So you can plug all that into your function generator. But you can do the same thing. If you're just working with sine, then you can just use this AC power. All right. Now, I believe there is a lab when we do our capacitors and inductors where we're going to use a square wave to get a DC response from our signal, which I know sounds ridiculous, but I'll explain it when it comes in chapter 14. Okay.